Hello and welcome to our lesson on rational functions in section 12.2. In this lesson you'll see how to identify excluded values of rational functions and also be able to graph rational functions showing all the asymptotes. And obviously we have some vocabulary to get through here. A rational function is a function containing an algebraic fraction where the numerator and the denominator are both polynomials and the denominator has a degree of at least 1. Now an inverse variation, which is what we looked at previously, they're the simplest type of rational function. You'll have a constant in the numerator, but you will have a variable in the denominator. All right, so again, thinking about this as a fraction, just think you have a long fraction bar, and you're going to have something in the numerator and something in the denominator. The denominator has to have an x at least. Can have an x, it may have x squared. In our examples, we're not going to deal with that. And the numerator can be a number, or it can be a variable as well, but we're just going to deal with constants in the numerator. Some examples that are not rational functions. We look here, we see an x in the numerator, that's fine, but we must have an x in the denominator. And since we don't have, in this case, even a fraction bar, we can't have one in the denominator. And since there's no variable here, we don't have a rational function. Now excluded values are any x values that make a function undefined. And for a rational function, an excluded value is any value that makes the denominator equal to 0. If you try to divide by 0, you have some problems. We don't allow those, therefore the things that make the denominator 0 are excluded because they make the function undefined. So find the excluded value of each rational function. To find the excluded values, we'll simply set the denominator equal to 0. And mentally you can do that. I'm not going to actually solve these equations or these expressions. Setting them equal to 0, we'll just state what they are. So if we look at the first one here, we have 3 over x. How do you make the denominator 0? Well, quite simply, you set x equal to 0. Why don't you guys try this one, hit pause, and see if you can determine what makes the denominator equal 0. Okay, if you look at it, anything minus 2 that equals 0, in this case, 2, x equals 2. We'll go down to the bottom here. We want to set the denominator or get the denominator to be 0. That'll make the function undefined. What value for the bottom example here? It's x equals 1. And then, of course, in this case, x equals 2 as well. All right, so whatever makes the denominator equal to 0. Some more vocabulary. A discontinuous function is one that the graph contains one or more what we call discontinuities, and those are breaks or holes. And a way to think about that is if you were tracing the graph, you'd have to lift your finger off the graph paper. So if we were to look at this example, this red, they call this a branch, this graph complete includes both of these sections. And I can't make the one side and the bottom left connect with the top right without lifting my marker. It's a discontinuity, and so the function then is discontinuous. And it is a function, however, if you think about it, it always passes the vertical line test. Okay? So it is a function. It's simply not connected. It's discontinuous. And if we go over here, this is a graph that if I had what we call a hole or removable discontinuity, that's a discontinuity. There's discontinuities that look like dash lines and circles. And in this case, we've got a couple of discontinuities here. We've got this dash line here. We've got a dash line that's vertical here. And again, these holes here. Okay? So graphically, we see what discontinuities are, and in the equation, we see how to make them happen. So if we look here, last piece of vocabulary, an asymptote, a line that a graph approaches but never reaches. It's represented by a dashed line. Okay? So if you remember when we did exponentials, this exponential here goes down. It's got a common ratio of less than 1, you could say. But what happens is this tails down to this dashed line of 0. It never actually gets to 0. and it's a horizontal asymptote. We call that an asymptote. And then in the example we saw earlier, these branches here are separated by what we call asymptotes, lines that are approached but never reached. So lots of vocabulary. Please make sure you keep this available and use it as you do work throughout on your own and when we get to class. And let's take a look at transformations of rationals with this information we understand. We can see that as a parent function, the 1 over x function looks like this graph. We've got vertical and horizontal asymptote and then the branches. The vertical asymptote occurs at x equals 0 and the horizontal at y equals 0, each of the axes. Now if we shift it left, right, up, or down, the h will be the amount we shift to the left or right, and the k is the amount we shift up or down. So in this case, since it's been shifted to the right 3 units and up 2, we see a minus 3 in the denominator, making positive 3 the undefined or excluded value. And then 2 is the horizontal asymptote. It's been shifted up. And in general, then, we'd see f of x equals a over x minus h plus k. It's got a, h, and k in it. We're familiar with that from parabolas. And we can generally say vertical asymptote occurs at x equals h and horizontal at y equals k. Let's do 3 functions here, 3 graphs, and see how it goes. Identify the asymptotes of the following rational functions and sketch a graph. In this case, the value of x that makes the function undefined is x equals negative 3, if you plug in negative 3 here. So out at negative 3, we would have an asymptote, vertical asymptote. And then we don't see it, but there's basically a plus 0 here. So the horizontal asymptote is on the x-axis. And we could sketch the graph with the 2 branches. This one's been shifted to the left 3. All right, similarly, we have a value of 5 in this case. That makes the bottom 0 and the function undefined. And again, the y equals 0. So if we were to sketch asymptotes, this one's for both of these was y equals 0, we would have the graph like this. Why don't you try this one as well? It's got one more change going on there. Okay, we see that we have a value of x equals 5 that makes the bottom 0 and the function undefined, and then a y equals 3 on the end. We sketch a horizontal asymptote at y equals 3, vertical at x equals 5, and then draw the branches. Remembering we have new branches to approach from the parent function, we don't want to try to approach the x and y axes. There we go. State the transformation, then graph. More of the same. We're going to state in words. In this case, for the first one, again, the left and right, up and down, it looks like x plus 4 in the denominator, and we always think opposite. So instead of right, we'd think left 4, and then the number on the end, minus 3. So if we were to sketch this graph, we would have a vertical asymptote at x equals 4, sorry, negative 4, and we'd have a horizontal asymptote at y equals 3, and then we sketch our branches. Now at some point we do care about those x and y intercepts where the graph crosses, but for now again we're really focused on just this family of functions called rationals. What the basic shape is, it's quite different than any other ones. It's got these discontinuities and asymptotes. So you're really, your goal should be to focus on what is the basic shape and how does it transform left, right, up, and down, and be prepared for a little more information about these graphs further in your academic career. All right, let's try this next one here in the middle. In your mind, say in words, and then write down, what do you think is going to happen? Is it going to move left or right, up or down? And then we'll go ahead and sketch that graph. Okay, we have an x minus 2 to get the denominator equals 0. We want to plug in 2, so right 2 and then up 3. So in this case, we have the graph, the asymptotes that we see, and then curves that approach but never quite reach the horizontal and vertical asymptotes. Last one here. Hopefully it's beginning to make sense here. The shape has stayed the same. It's just the dashed lines that move around. Think for a moment, hit pause, do your best work, and then come back and see how it goes. All right. This one moved left 6, the bottom to be equal to 0, had to be a negative 6, and then down 4. And so we've moved left 6, and we're going to have a vertical asymptote to the left 6, and then also down 4, we're minus 4. And now we sketch these branches. And now that we've looked at equations and sketched the graph, let's try working the other way here. We've got the graph. Let's see if we can find the equation. And it's worth remembering what the basic function looks like. It'll look like this, approaching the x and y axes, because if it doesn't translate left or right, up or down at all. But in this case, it's moved right, up as well. So right and up in this case gives us an equation x minus 2, it's moved right 2, and up 5. Come over here. Why don't you try this one on your own. Notice there are no pluses or minuses in there. You have to determine left, right, up, and down from the graph and put in the right values. Okay, hopefully you've tried that. In this case, we've moved right 3, so x minus 3, and then now down 2, so minus 2. Remembering the opposite of what we might think for x, and then what we'd think for the vertical. All right. These are the on your owns. Give them a try, and we'll see you in class.